cloud. Yeah, everything is fine. That's well. Lecture. So we'll start something about game theory. There are many parts of game theory. We will focus mainly on non-cooperative games. So we will study non-cooperative games. That means that every player has its own goals, and he has basically, he or she, he has her or his utility function, and he tries to maximize his utility function. We will not deal with games where players have the same goal, and the main question is the formation of coalitions. We will study non-cooperative games. Okay, and let's start with, probably you have already encountered some concepts from game theory like Nash Equilibrium and so on. So we will formalize them, and we will solve some examples of games. Because basically, from mathematical viewpoint, game theory is just a maximization of many functions at once. So when we study optimal solutions, we have one function, some constraints, and we maximize it. And now we have many functions because each player has his own function, and we have many functions to maximize simultaneously. So basically, it's maximization of many functions at once, if we speak in a very simplified way. So basically, game theory is to optimize many functions at once, but these functions have conflicting goals, have conflicting targets. Okay, let's start with formalization a little bit. So we consider a simultaneous game. We will have the set of players. From mathematical viewpoint, we will work with a simultaneous non-cooperative game. Okay, we will have I, that will be the set of all players. Yeah, if you have any suggestions, just to zoom a little bit in, or to zoom a little bit out, bigger font, smaller font, just don't be shy, tell me, because it's unexpected for me that Zoom does not pick up the application where I'm usually writing lecture notes. So that's, I don't know why, maybe some change in the policy of Zoom, because they are refusing corporate clients in Russia to continue corporate accounts. So maybe something else, I don't know. So if something is not visible clearly, then just tell me and I will make bigger font. That's
yeah, could you zoom a little bit?
Yeah, don't be shy. Okay, yeah. Even we can oh, I can do it here. Yeah, like that. Maybe it's oh yeah, let's make smaller box fields but bigger normal text. Yeah, like even I can write here something like, or maybe 200. Yeah, and even that field I can make tree style tab. I don't need it, honestly. Okay, yeah, and even bigger. Yeah, no, it cannot be bigger than 200%. Okay, Google has some limitation. Yeah, I is a set of all players. It may be infinite, but we will consider games with 2, 3 agents, but it may be infinite set. Okay, each player will have a set for each player I from the set of all players. We have well, that's a definition. Yeah, definition. Simultaneous game is a set of all players. For each player I from the set of all players, we should have the set of possible strategies, the set of available strategies or moves in a simultaneous game. So in a simultaneous game, that is the same thing. Strategy is a move, is action. So in a simultaneous game, it's the same thing as action, move, because we have only one move in simultaneous game. So they simultaneously make their choices and they receive a payoff and the game ends. But in a consecutive game, a strategy and move are different concepts, because strategy is an instruction that explains me which move I should take in every possible position. But for simultaneous game, the set of strategies for every player is just a set of available actions. Action move is a synonym of strategy in a simultaneous game. In a simultaneous game. Okay, and for every set of available strategies, yeah, that's for player. And when each player make a choice, they receive payoffs. So we have a payoff function, utility. Yeah, let it be small. Yeah. The utility function of player number I, and this utility function is just, yeah, and maybe I can insert equation. Yeah, yeah, I can insert equation. UI of S1, S2. Yeah, I can write equation. Yeah, I'm happy. L dots Sn. So this is a utility function of each player, depends on the choice of each player. Yeah, we can insert equation. I'm great. UI, and that will be SI. Basically, that's a game. We have defined what is possible to do. We have defined what are the consequences of your actions. That's all. And we needed to predict somehow how will the game be played. Okay, so we need, so our goal, our main goal to predict the behavior, the behavior of all players. So that's our main goal. Okay, so let's provide an example, and I will ask you to guess what will be the behavior of all players. Imagine two players, Alice and Bob. So we have two players. We have Alice and Bob. And they have found a magic box. They have found a magic box. They have found a magic box. So they simultaneously should put in this magic box any amount of money they wish. So Alice and Bob simultaneously put any amount of money in the box. So, and then magic happens, and the magic box will calculate the average amount of, so the magic box will calculate, I think that, yeah, it will calculate the average amount of money, will calculate the average, will automatically calculate the average, multiply it by, I think it will multiply it by I think the magic box has no problems with printing money, so it will multiply by a factor of, I think by a factor of 3. By a factor of 3 is enough. Okay, it will automatically calculate the average, multiply it by 3, and it will distribute this sum to Alice and this sum to Bob. So it will calculate the average, multiplied by 3. Let's call this value, let's call this value by, let's denote this value by V. Yeah, by V. And Alice and Bob and the magic box will give Alice and Bob this value, this sum V. Okay, the setup is clear. Alice and Bob, so we have a magic box. Magic box is like that, magic box. You put their money simultaneously, and boops, ahalai mahalai, every player magically receives the average multiplied by 3. Okay?
Yep.
Yeah, that's clear.
So they simultaneously put any amount of money in the box. They say ahalai mahalai, and everyone magically receives average multiplied by 3. Not only Alice, but Bob also. They both receive the same amount, V. And V is the average multiplied by 3. Okay, and my goal is, I have 2 goals. First goal is to learn to formalize the abstract idea into a mathematically correct, mathematically strict object. And then let's try to predict what will happen. So we have 2 goals. We have one goal to formalize it as a formal simultaneous game. So, okay, let's do goal 1. Let's formalize the game. So it's a little bit boring, but in a complex situation, in situations, that's an important step to have a clear formulation that can be solved by some strict mathematics. So let's formalize this situation. So what is a set of players? So what is a set of players? I is equal to what in this game?
Alice and Bob.
Alice and Bob, yeah.
Yeah, we have Alice and Bob. Okay. Yeah, that's the set I of all players. Okay, now let's describe for each player. So for player A and for player B, we should write a set of available strategies. Basically, what Alice is choosing. She may choose amount of money to put in the box. Okay, what are the possible choices? So here we have a little bit of freedom, because in a text it isn't described whether money is infinitely divisible, or we have some small like pence, or so maybe there are smallest units of money, but maybe money is infinitely divisible, so we may consider that or this formalization. But in my case, let me imagine that it's not possible to, for me, it would be easy to work with infinitely divisible money, but the resulting game will a little bit different, but the result roughly will be the same with infinitely divisible money, or with a situation when we have smallest unit of money. So let's imagine that we have the set of available actions, the set of available strategies is from 0 up to plus infinity for player A, for Alice. And basically the set of strategy is the same for Bob. Okay. And now let's write the utility function. So what is the utility function of Alice? Utility function of Alice that depends on the amount of money that Alice has put in the box and the amount of money that Bob has put in the box. So what is this utility function? So imagine that, let's pretend that each unit of money has constant utility. So we will not deal with the case where she has some risk preferences. So in this case, we will consider the case where each unit of money has the same utility. So what is the utility function for the player A? And what is the utility function for the player B?
It's the same.
No, they are not the same.
I think if we do not restrict our constraint, it will be infinite utility. I mean, it seems to me. If we do not restrict our constraint for SA and SB, they might be infinite utilities, as they can.
No. I'm not speaking about for the moment about. So we have two processes. First process is to formalize the game, and second process is to predict. So for the moment, I'm in a stage of just describing from strict mathematical viewpoint what is possible. For the moment, I'm not trying to predict what will happen. I'm just trying to formalize what will be the payoff, the profit of Alice if they choose to put SA and SB in the box.
If I understood correctly, it should be the sum of SA plus SB over 2 multiplied by 3.
And minus SA or minus SB, because these are the
Yeah,
costs.
exactly. You should not forget to have a minus. Okay, so we need to have here SSA plus SB over 2 times 3, yeah? And do not forget to put minus SA. Okay? And here's the difference is we have SB here, okay?
Yes.
Yeah, okay.
Yeah, that's a formalization of the game. Okay, and let's try to predict what will happen. So that's a formalization. So now this is, so to formalize a simultaneous game, what we need. So the first process is finished. So we try to say, what is a set of players? What are the available choices for each player? And the important moment is a utility function for every player choices of all players, including that player and other players of the game. So because there may be 20 players in the game. Okay, so yeah, that's a formalization of game. So what is a game? Formally is a game. Formally is a collection of I, S, A, S, B, U, I, and U, B. So a game basically is a collection of these objects. Okay.
Could you
Yes.
please explain one more time, why did you subtract SA and SB from the utility functions?
Why? If you are not subtract SA from the utility function, let's play the following game. You will give me 20,000 rubles, and I will give you 100 rubles. I think it's a good game for you, because I give you 100 rubles. That's a good game, yeah?
Ah, yeah. Yeah, I understand.
I'm waiting for your sum, and that's a profitable game for you. Believe me, I will pay you 100 rubles.
Yeah, thanks.
Yeah. The main reason that we basically our players may have a very short memory. Yeah, they may say, "Whoa, I'm happy with the total revenue." Yeah, but normally in economics we assume that agents are interested in net profit, not in. So yeah, it's a little bit. Yeah, that's why we formalize. Yeah, I agree with you that we need to formalize to avoid such confusions. So basically, it's not. I haven't written explicitly that they are maximizing net profit. Yeah, that's exactly why the formalization stage is needed. Maybe Bob just wants to make a present for Alice, and maybe the utility function of Bob is just the same as the function of Alice. Yeah, maybe. And so he interested that she will receive more money. Maybe. So so that's why we are formalizing in mathematics, to avoid confusions like that. So that's why that stage is important. Okay, and now let's try to predict. Let's try to predict. What is your prediction? What is your prediction? How this game will end? Let's predict. What is your prediction? What will be the result of the game?
Well, each dollar, let's say, put in the box, give the payoff of 1.5 to each player. So
Yeah.
if someone puts additional dollar, it receives 1.5 back. So
Yeah.
everybody should put in the box as much as possible.
Yeah, I agree with you that if we have say, so let's limit the right-hand side to have an equilibrium. Let's say they have 1,000 rubles each. So let's do like this. And we see that from this, so our prediction is very simple, that our prediction will be that SA will be equal to maximum available amount, and SB will be equal to maximum available amount. Yeah, I agree with you. That's a good prediction because we Yeah, I agree with your logic, but we need a concept to easy to calculate in every possible context. So we will introduce formally the Nash equilibrium, but for the moment, before introducing it, let's consider one more case. Let's change this magic box a little bit. So I will change magic box 2. No, I will go on the next page to avoid problems. Magic box 2. This second magic box is a little bit greedy. So it calculates the average and it multiplies by it multiplies, let's say, by 0.8. Yeah. So we change here. Our new magic box has other properties. So our new black on red. Yeah, that's the change. We have another. The second magic box has a little bit different magic. We may see that the second magic box also prints money. So basically, if everyone puts 100 rubles there, everyone will receive, I know, so if everyone, no, I need, no, one, it will, no, it's a bad box, no, one by 1.2. Yeah, I think like this is okay. Because it was an awful box. I will never put money when it's the average is multiplied by 0.8. Yeah, let's consider a box, a second magic box, which increases the average by 20% for free. Yeah, we have another magic box, second magic box, that increases the average by 20%, and everyone receives this increased average. So what is your forecast? What is your prediction for the second magic box?
Well, if they are good friends, then they can still put all the money and it will be profitable for them. However, if we consider them as selfish, let's say, so they shouldn't put the money in the box.
These values. No, this. Yeah, I agree with you completely. This value. Yeah, value. Okay. Well. Yeah, I agree with you that if everyone, so we are studying, once again, we are studying non-cooperative game. So what does it mean for us? It does mean that everyone is choosing for himself or herself, and there are no other consequences as this payoff functions. Everything is formalized there. And so if I just simplify these utility functions, in the second game, Magic Box 2, I will get that if I divide 1.2 divided by 2 is 0.6, so it will be 0.6 SA minus SA plus SB 0.6. And finally, I will have, if I simplify this expression, I will get 0.4 minus 0.4 SA plus 0.6 SB, okay? If I just simplify this expression.
Okay.
Yes.
And now I can clearly see that what the first player is doing. The first player, player A, is choosing the value of SA. In a cooperative game, there may be some agreement with the player B that, okay, I promise you to choose if you choose. But in my non-cooperative game, either this talk is impossible, either you have no consequences when the agreement is violated. So because everything is described by this payoff function. And so if everything is described by this payoff function, and I think I cannot influence SB, SB is chosen by player B, I'm player A, I choose SA, and I look at this function and I see that the function depends on my choice with negative coefficient. So the bigger is the sum I put in the box, the smaller is my net profit. Yeah. Okay.
Okay.
Can you see it? So the bigger the sum I personally, player A, put in the box, the smaller is the sum I get as a net profit. Yeah. We
Yeah.
are interested in the net profit.
Sorry. So here,
Yeah.
the assumption in that place is the sensitivity for human brain of the change in numbers is totally relevant to the real amount change in calculation. Is that right?
Sorry. What's wrong?
I want to know the sensitivity here for the human brain of the changing of the index at that place is totally equal to the real calculation in mathematical pattern of the change in the amount, right? Because human being about the change of the number is different compared with machines and the calculations.
Yes. I understand that we have a lot of we are poor human beings and we have a lot of psychological traps and so on, but my players are perfect optimizers and they can calculate everything without errors. Yeah, I assume that my players are interested in maximizing the utility function, and that's all. And they
Yes.
have no problem with solving any complex math problems. Yeah, that's important assumption. I agree that we need to talk about to predict the behavior, or maybe not of some idealized players that have infinite computational power and so on. Okay, so our prediction changes in that case if our players see that on my choice the function depends in a negative way. So the less I will choose, the bigger will be my payoff. And basically the prediction for that's important, that we're studying non-cooperative games. Yeah, they have no legal, like players cannot make a legal agreement like if you will not put 1,000 so you will be prosecuted. So that's not okay in a non-cooperative game. So in a non-cooperative game, players only bother about their personal utility function. Okay, so and the prediction here is completely changed. So we have the prediction that in a non-cooperative situation, the choice will be 0, 0. And it seems strange at first because our magic box prints money. So honestly speaking, there is a possibility to make profit. Yeah, if everyone will put 1,000 rubles in a box, then everyone will receive 1,200. So the average of 1,000 and 1,000 is 1,000, and everyone will get back 1,200 in that situation, and it seems profitable. But every player has incentive to deviate from promise to, yeah, let's put 1,000, let's put 1,000, and Delis thinks, oh, if I will put less, I will receive more because my function has a negative coefficient before the variable I'm choosing. Okay, so now let's formalize the concept we need. So second definition, some definitions. So we will say the profile of strategies. Or we say sometimes outcome. Profile of strategies is just a name for S, A, S, B. Maybe we need to write first in general. So the set, the vector of strategies, the vector of strategies for every, and the vector that assigns one strategy for every player. Okay, that's a profile of strategies. In our example, the profile of strategy is just a vector SASB because we have two players. And we have definition Nash equilibrium finally. Nash equilibrium is a profile of strategy. So there are many definitions of Nash equilibrium. They are equivalent, obviously. It would be strange that a mathematical object has conflicting definitions. So the first possibility that we say that the profile as, so let me have let me introduce some other notation. So let me introduce some more notation before introducing Nash equilibrium definition. So I will, maybe it's better to write notation, yeah, notation. I will write by S with index -a, I will denote the strategies of all other players except player A. Okay, S-A is a vector of strategies of all players except player A. Okay, because when I have 20 players and I fix the strategy of the second player, it will be convenient to write something like S-2. That means not the player number -2. That means player number 1, player number 3, player number 4, and so on. So by S-A, I will denote the strategies of all other players except the player A. So that's just a useful notation. And now, finally, I'm ready to give a formulation of Nash equilibrium. Definition. Nash equilibrium. It's a So it's a profile of strategies. So it is something like in a game of n players. So in a game of n players, I have S1, S2, S3, and so on, Sn. So it's a profile of strategies where none of the players can do better by choosing his or her strategy alone, where no one can do better by deviating, by changing his strategy separately. I will just add some electricity. Okay, so Nash Equilibrium is a profile of strategy where the utility of every player given the strategy of that player and strategies of other players is greater or equal than the strategy of this player number I in the case of deviation. If he deviates, so he will choose some strategy, let's call it S, what is it, SQRI. S minus I for every R and for every player, I and for every strategy, RI and for every player I. Okay, let's discuss a little bit this definition. So basically, what does it mean? Let's consider player I. It says that by changing his strategy, by playing R instead of S, this player cannot do better. If he chooses to play R instead of S, fixing other players' strategies, then he will receive less or maybe the same amount of money as in the case where he play SI. Okay, any questions?
No questions, that clear.
Okay, and let's check that in our two games, Magic Box 1 and Magic Box, so it will be Magic Box 1. And in Magic Box 2, indeed, these two predictions is just a Nash equilibrium. Indeed, so let's check that this is just a Nash equilibrium. Yeah, so we know that example continues. S1 is Nash equilibrium in Magic Box 2. And if every player chooses 100, then it's a Nash equilibrium in Magic Box 1. It's easy to check, yeah? For example, if I fix so let's check. Let's check, for example, that 0, 0 is a Nash equilibrium in Magic Box 2. Let's check this statement. And now we will consider something more interesting. So let's check that. Okay. So first we fix the strategy of the second player. So let's fix. Let's fix SA equal to 0. What is the best? What is the best SB? And if we look at the equations, we see that in the second equation, it looks like 06SA minus 04SB. And if we fix SA, then the best SB is 0. So if we fix SA, so why we fix other player strategy? We have a definition. So S minus I is fixed in the definition. We have S minus I in the left-hand side, S minus I in the right-hand side. And when we fix S minus I, and the best thing is SI for player I, not any other RI, but SI is better for the player I. For the best SB, and best SB equal to 0. And vice versa. Let's fix SB equal to 0. What is the best SA? What is the best SA? The best SA is 0. So basically, 0, 0 is a Nash equilibrium in a game Magic Box 2. Okay, any questions?
No, everything is clear.
Okay, let's move on. Now let's consider some more terms. We will use the term best response. So let's provide a definition. Best response function for player I is a function that takes every possible combination of other players' strategy and gives the player I recommendation what is better to play. Yeah. So basically, best response function for the player I describes what is better to play for the player I given the choice of all other players. So best response function of the player I describes the best choice of the player I when we fix when we know the choices of all other players, and we will denote it by, so from formal mathematical viewpoint, best response function of the player I takes the set S minus I, and it, why it's not 2? Why it's not 2? 2. Oh, why it's not working? Okay, I will insert special chapters. No. Okay, I will write R like that's the set of real numbers. So best response function of every player describes the best choice of the player I when we know the choices of all other players. So the choices of all other players is S minus I. Minus I means all players except player I. And we may say alternative view of Nash equilibrium. So that's important to say that best response may be a set if you are indifferent between two options. Someone asks you whether you prefer tea or coffee, and you say, "Oh, I'm indifferent," and that means best response function can be, the result is not one value, but the image of best response function. This may be a set. Okay, that's important point. So when you are indifferent, best response function will give you all choices, all best choices. Yeah. So alternative view of Nash equilibrium, we say that this is a profile of strategies. This is a profile. Oops, I will go on to the next page. And this is profile of strategies where SI belongs to best response of all S minus I. So my action, my strategy is the best response for other strategies, for all players, for every player I. It's better to say like this, for every player I. Okay, so that's basically the same thing, because what is written here, with my current choice SI, I receive not less than with any other choice RI. And this says that my choice SI is the best I can do given fixing the strategies S2, S3, S4, and so on, Sn if I'm the player number one. Okay. Yeah. Can we go?
Yeah, let's go.
Okay, let's continue. Now let's introduce a little bit of probabilities into our setup. Okay, now we will introduce mixed strategies. So sometimes we will allow players to randomize, to say, yeah, not only you can choose A or B, but you can choose A with probability 0.3 and B with probability 0.7. Obviously, we will not violate the laws of probability theory, but we allow players to randomize their choice. Now we allow players to randomize their choice. Allow players to randomize their choices. So what does it mean? In our case, in a game of Magic Box, Alice now may follow the strategy like, I will put in the box 100 rubles with probability 0.7 and 200 rubles with probability 0.3. So we allow players to randomize, okay? Yeah?
Yeah,
Yes.
okay.
Okay, what will change if we allow players to randomize their choices? So now every player, first we need, so what will change in our game? So in our game, the set of available strategies will be bigger, because if, for example, I have two choices in a non-randomized version of game, I can either, let's say, put 0 or 1000. So let's imagine a game where you can put only 0 rubles in the magic box and 1000 rubles in the magic box. In that case, we have two choices. And in a randomized version of game, you can put 0 with probability 0.3, 1000 with probability 0.7, or boss with probability 0.5, or 0.9 and 0.1, and so on. You cannot violate laws of probability, but you can randomize. Okay, so in this case, we have we will introduce in this case the set of strategies of every player will be bigger. Yeah, will be bigger. So let's denote the randomized set of strategies. So we denote the set of randomized strategies by, and normally it's by delta. Why it's not transformed into big delta? Oops, I think I'm lost. Just a moment. I hope it will reconnect. Ooh. I think I'm back. Yeah, I hope everything is fine. And we denote the set of randomized strategies not by S. This S will be the set of non-randomized strategies. And now we will denote it by boom, 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 boom. Yeah, I have a big delta here. Yeah. Oh, what's going on? Sorry, can you hear me? Because I don't know what's happening with HSE
Yes,
network.
yeah, I hear you. I can hear you.
Okay, thank you. Yeah, I don't know. I'm using HSE work network Wi-Fi, and it stops working. Okay, so I will denote the set of randomized strategies of the player I by delta I. Delta I is bigger than SI. SI may consist of two strategies, and delta I has infinite number of strategies in any case, because even if I have two original strategies in SI, then I have infinite number of strategies in delta I. To distinguish them, I will denote, we will introduce terminology, strategies, original, non-randomized strategies, non-randomized strategies from SI. We will call them pure strategies. SI, we will call them pure strategies, and randomized strategies from delta I, we will call them mixed strategies. Okay, The terminology is clear?
Yes.
Okay, and now basically what will change? So in a definition of the game, we have only one change when we allow randomization. We have one change. The set of all players is non-random. The set of available strategies is now it is bigger. It's delta I. And we require once again that every player has a utility function. And we will have a change. So the main change is here in the definition when we allow randomization. Now we work not with SI, but with delta I, the set of randomized strategies. And what will change in the definition of Nash equilibrium? Nash equilibrium is because the payoffs are random now. Then players are trying to maximize expected payoff. So when players do randomize, so the main change that the expected payoff is bigger profile of strategies, and let's it's called delta 1. Yeah, it will be delta. Why it's not putting small delta? Why it doesn't know about like there? It's delta 1. So players now are using randomized strategies, not pure strategies, or maybe pure, but they can use randomized strategies. Okay. Beep, 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 beep. And now let's delta I delta. Okay.
Sorry, I have a question. So if the randomized in here is predictable, it's not called randomized. Randomized is some kind of unpredictable without the calculation or out of the control of the calculation.
Randomization means that I'm choosing one of the pure strategies. Pure strategies are strategies from S. So I'm choosing one as a player. I'm choosing one of pure strategies at random with some probabilities, and I'm optimizing with respect to probabilities. So let's consider an example. Maybe it's better, as always, to consider an example. So let's consider what is called B matrix game. I will insert a matrix. Yeah, we have two players. So player A can choose, let's say this will be strategy A. This will be strategy B. The second player can choose between strategy C and strategy D. So normally we write first player is a row player and the second player is a column player. And payoffs, this is a simultaneous game. We study for the moment only simultaneous games. So they choose simultaneously. First player will choose A or B, but he is allowed to randomize. The second player chooses C or D, but he is allowed to randomize. And the payoffs are, let's say, I don't care, 10, let's say 20, 20, let's say 0, 0 to simplify, let's say 0, 0, and let's say 10, 10. Their payoffs are clear.
Mm-hmm.
So if they simultaneously choose A and C, boss will receive 20 rubles from the casino. If they simultaneously choose B and C, everyone receives 0. If they simultaneously choose B and D, everyone gets 10 rubles, okay? And in this game, I say people can randomize. So for example, first player can use the following randomized strategy, mixed strategy. So the terminology is mixed strategy and pure strategy. So what does it mean, mixed strategy? I can play with the probability P. I can choose, so I will denote the probability here by P and Y minus P. And the second player also is allowed to randomize. So the probability is Q, and to not violate laws of probability, 1 minus Q. Okay? And my goal is to find Nash equilibrium in mixed strategies. So my goal is to find Nash equilibrium or Nash equilibria, maybe there are many Nash equilibria, in mixed strategies. So every player can randomize. Okay?
Okay.
So now let's work with this definition. So I will calculate expected profit of the first player. So expected profit of the first player, row player. Yeah, the first player. So the standard numeration is first row player is a row player. It's agreement old agreement first player chooses rows. That's all agreement. So the expected payoff is 20 times PQ plus 10 times 1 minus P, 1 minus Q. Okay? And it's plus 0 times P times 1 minus Q plus 0 times 1 minus P times Q. And if I simplify this expression, I will get 30 PQ minus 10P minus 10Q plus 10. I think like that. Yeah.
Absolutely correct.
Okay, so now I can find best response function, because to calculate Nash equilibrium, I need to find the best response function. Okay, I can find. Okay, so let's find the best response function for the first player. A best response function for the first player. It depends on Q, on the choice of other player. Yeah. Once again, let's look at the definition of best response function. The best response function of player I, it's instruction to the player I what to do depending on the strategies of other players. Okay, so best response of the first player depends on Q. And basically it says, do I have some bracket? Yeah. I don't know. Okay, I will write in this bracket, but maybe that's not I'm searching for. Can I have double? I don't know how to. Okay, I will write. So I will write like if. So I see that I can restate my. Oh, sorry, we have almost no time. So okay, let me be quick. Okay, I will take out P out of my formula. So it will be P times 30Q minus 10 plus 10 minus 10q. This part of the formula, 10 minus 10q, I cannot influence. I'm choosing p, so I cannot influence this term. So this is like a constant for me. And I can influence only what depends on p. And I see that if 30q minus 10 is greater than 0, then the best choice is 1. So if the term that is multiplied by p is positive, then I'd like to choose p equal to 1. If 30q minus 10 equals to 0, then the best p is any value between 0 and 1. And if 30q minus 10 is less than 0, then the best p is 0. That is the best response function for the first player. Because my game is simple, it's symmetric, so I can just write the same function for the, I just interchange p and q, and I have the best response function for the second player. What is the optimal action for the first player, for the second player, given the action of the first player? So I have two best response functions. Because my game is symmetric, so they should be, the best response functions should be symmetric. For non-symmetric matrix, obviously, we have two different best response functions. Everything is fine?
Everything is fine.
Any question?
No
Yeah, I have a
question.
question in here. So that means with the higher intelligence of the partner, the probability the other side will betray me will increase.
Yeah, if Q is very big, then I'm interested in a big P. If Q is very small, then I'm interested in small p, in P0. That seems more or less natural. Okay, and we draw. Let's draw how we can drawing. Yeah. Let me draw something like so that will be the set of all pieces. So that will be text. I have P there. I have, so my drawing is not perfect, but okay, let's have P on the horizontal axis, Q on the vertical axis. And basically, if if Q is 1/3, then we're indifferent. So if it's 1/3, basically 1/3 is like that. 10/30, it's 1/3. Then we are indifferent. If Q is too small, then so can I choose okay. And I will draw one more line. If Q is small, then P should be 0. If Q is big, then P should be equal to 1. And let me change the color. So the best response function for the second player, I will draw in blue. So when Q is 1, when Q is 1/3, then P I have any number. If Q is big, then sorry, if P is big, then I have Q should be equal to 1. If Q is small, I should have if P is small, then I have Q equal to 1. And basically, I have too many blue color. Let me change the color of that line. And basically, I see that I have it should be black. So the best response function of the first player is black. The best response function of the second player is blue. And basically, oh, it's awful, but it's okay. It's okay. For me, it's enough to say that I see that I have 3 mixed Nash equilibria. So I have, so the final answer I have three mixed Nash equilibria. The first one is P equal to 0, Q equal to 0. The second one, where best response functions do intersect, P equal to 1, Q equal to 1. And the last one, P equal to 1 over 3 and Q equal to 1 over 3. So basically, from this plot, I see that I have 3 points where my action, my strategy is best response to the second player strategy, and second player strategy is best response to my strategy. And I have 3 mixed Nash equilibria. Okay.
Yeah, could you please upload the lecture and also the Google Doc into the
Yeah, I will. Yeah, let's do it just now. I will share lecture GT1 name before sharing. Okay. So now I will copy link and I will just
or also to the Telegram channel.
Okay. Chat. I think here it is. Okay, and in Telegram channel. Okay. So basically that's all. So what we have defined today, we have defined simultaneous game. We have defined best response, profile of strategies, Nash equilibrium. Then we have defined randomized version of a game when we randomize over pure strategies. In this case, the set of strategies is bigger, but the definition of Nash equilibrium is exactly the same. We just put expected value, and every player maximize his expected utility by choosing his mixed strategy, keeping other strategies fixed. That's all for today. Next time we will continue with game theory with more complex problems. We will not, I think, introduce more language, but we will study more difficult problems. I'm not sure whether the link for Zoom will be the same, because we have some problems with Zoom restrictions in Russia. We have corporate accounts are canceled, and so either I will buy my account, either we will go to MS Teams. I don't know yet, because I don't understand why I can share the screen of my tab and I need to draw. Okay.
Excuse me, I have one question. In the middle of our lecture,
yeah,
in the middle, there's one strategy is follow others player strategy without except player one. What does that mean?
Oh,
The second example for B will yeah here.
S minus A, the strategies of all other players except the player A. So if we have only 2 players, then S minus A is just SB. But when you have 3 players, so maybe we should add example. If you have 3 players, if we have 3 players, A, B, and C, then by S minus A, we just denote SB and SC. Yeah, like that.
Okay.
Okay.
So that means player A take a disadvantage, or B and C was
no. We don't discuss the advantage. So it's just a notation. When you have, instead of saying SB, SC, you say S minus A. So the strategies of other players. We don't speak about the advantage. So it's just a description how to write strategies. Instead of writing 2 letters. You write 1 letter, but with minus. If you have 20 players, to say, I'm fixing the strategies of the player number 1, 2, 4, and so on, you say, I'm fixing the strategies S-3. So S-3 just means all the strategies of all players except the player 3. It's not about optimality. It's just a notation to denote the set of strategies. So instead of writing, I don't know, so I will write like, it's not about the advantage, it's just about the notation. S minus B is just the strategy of the first player and the strategy of the third player. Just a compact notation.
Okay. Okay.
Okay, see you next time. Have a nice.
Sorry. So if I want to know more information about the tasks from here, is there any website, any YouTube channel, or any kind of PDF book I can have a read?
What is the best choice? I think the best book is there are a lot of books on game theory, obviously. My personal choice is a book by Osborne Rubinstein. But there are a lot of books on game theory. Osborne Rubinstein, Introduction to Game Theory. I think it's one of the best introductory books, but there are a lot of sources. So if you just Google game theory, a lot of sources. So that's a good option to avoid lectures completely. So that's an excellent book. There are many other books. So I'm not limiting your choice. I'm just saying that's a good source, but there are many other sources. So
Okay.
Thank you for the lecture. Bye.
okay, bye-bye.
Bye, Boris. See you next time.